So T15 has its correspondence to T16, which is SMAN, which is nothing but the T15 15th element and the next one. So we have to find out what is the index in the suffix array. So let us see what happens here. T16 is SMAN, and we find out that over here it is so we have to find out where the 16th value comes in. It is at 14. So this is the suffix array, and we have to find out which is the specific index where it occurs. So we find out 14 is the index of the suffix array. So we updated A14. Similar for T0, we have H, and 05, we have N02. So essentially we've managed to shorten this. Now the next part is like T21. So we have like all the different we've found out these things. Now we have to sort out this specific part of this question. So T21 comes at the start, which is 00. Then T18 comes after that, which is A10. T15 comes after that, which is A14. So these are also lexicographically sorted. So this can be done in O of n time. The next step is to merge it. So once we found out these things, then we can essentially follow the third step, which is like merging all of these things together. So it seems simple till now, but the only problem here is that we've not taken much care about the first problem, which is computing a rank array R12. So we have a remedy for that. We're going to discuss how it is done. So here we go. So so if we consider the first triplet, we have T1 and T2. So what we do is we create triplets inside it. So we chop off the first element first and foremost. So we're just concerned about everything in this string except BH. So ANN, AHB, ANS, BAN, and all of these things are parts of the first string. So these are the triplets that are formed inside T, and these are the triplets that are formed inside T2. Now what we do is we create a combined list of these triplets that we've found out. So there's to my knowledge, we can see just one triplet which is repeating while the rest aren't. But when we are dealing with longer numbers, much larger strings, I'm pretty sure we'll find out more recurring strings. However, in this example, we don't have a lot. So again, once we find that, we lexicographically sort that, and then we rank those. So as you can see, it's ANN, AHB, ANS. So AHB should be coming at the start. So AHB is at the start, which has the index 1. ANA and ANN follow after it. So all of these is lexicographically arranged. So this is how we find out the index for it. So what we're dealing with is not this T dash, which is the string itself, but we are more concerned about the indexes. So we're concerned about the T double dash over here. So that's it. So we found out how to create a suffix array, which should be done through an optimal method, and the best method is the DC3 algorithm. Now we move on to the second problem, which is the longest prefix array, and we can do this through a naive approach. Like we can calculate the LCE of two consecutive elements while we move from I is equal to 0 to I is equal to n minus 1, where n is the n is the total size of the array. But that wouldn't be a good approach, because as you can see, comparison in every single step isn't ideal. So alternative approach is to check out all the leaves, but we've seen before checking out all the leaves in itself is a problem. So we have to go to every single leaf in a tree, and then we have to find out uh, what the corresponding uh, substring suffix string is formed. Uh, this is not the most optimal solution, as you can find out. So we have a novel algorithm which is called Kasai's algorithm. And here are the steps for Kasai's algorithm. We have a suffix array and the original string. So suffix array was constructed in the previous step, and we also initialize an auxiliary array, so which stores all the indexes. We also have an LCP array. So this algorithm is inspired by dynamic programming. So we also store something like LCP 1 to n minus 1 to store the results that we have. We'll find out more about this through an example, as it would be easier for us to understand it through an example. So when you find out the main string, the string that we have, so banana ban is the biggest string that we have, the entire string, you might say. So we find out the corresponding position of banana ban in the suffix tree that we have found out. So it if you think about it, every banana ban is the largest substring that we can have of the string itself. Of course, since it's the first substring, uh, there are no chopping off of indexes in it. So here we have it at index number 6. These are all lexicographically arranged as a suffix tree should be, suffix array should be. So what we do is we compare it with the element that is just above it. So logically, if you think about it, every suffix array should have common things uh, with other substrings which are close to it. So banana ban is a substring, and another substring is ban, which is ban, and it is positioned just one index above. So we can pretty much all we have to do is pretty much just uh, compare both of these. Now, so when we compare it naively one by one element, so we find out that 3 is the largest number of the 3 is the largest prefix. So when you compare banana ban with ban, we find out that 3 is the longest common uh, prefix of this. Then we store 3, and we have to keep in mind that we have to keep in track of this number, so we can create an integer which keeps track of this. So 3 is our longest substring till now. Again, as we move forward, we're done with the with the entire element. Now we move on to the second largest substring, which is banana ban, and again we go through the same procedure. We create we find out its corresponding value in corresponding index in the suffix array, and then we compare it with what is above it. So banana ban has one substring above it, which is anaban, and we find out that the first three so the first three elements are the same, so we also can write down 3 as the suffix value. uh, we also have to keep in mind that we're thinking about we're thinking about this. So when we're thinking about banana ban, we already have searched for values that start with B. So we have to discard it for this procedure, and then we have to move ahead with that. So since we're using dynamic programming here, we will have kept track of this uh, through an array that we've talked about in the previous slide. So an is what we have already stored. So an will already have a value of 2 stored in it. So anything that is common after a should be incremented. So a is found out. So an is already 2, and we find out one element which is common after that. So we will just find out 2 plus 1, which is 3. So this is the longest common prefix, and eventually if we do this for uh, all the entries in uh, our substring table, let's say, or the suffix array table, then we can find out what are the different LCPs, and then we can pretty much see that 3 is our longest common prefix here, and which is what our answer should be. Now I think we've found out the solution for this. Now let's consider what is this algorithm efficient. So firstly, we saw the DC3 algorithm, and you might have found out that it is much more efficient to use DC3 than it is to create suffix trees and then uh, do all those calculations. So it takes O of n log n time. Again, computing the LCP, it can be done in linear time. So O of n log n plus O of n, it is in the range of O of n log n. So the overall time complexity of this approach is O of n log n. And I am pretty much sure that this is the best algorithm, and this is the best way to approach this problem. Thank you.